The most terrifying part wasn't the explosion. It was the silence before it. No alert, no warning, no countdown. Just an ordinary Tuesday morning in Ohio. And then, without a single system on Earth saying a word, a 7-ton rock from space detonated overhead with the force of 250 tons of TNT. Buildings shook. 911 lines flooded, and every planetary defense telescope on the planet missed it completely. Here's what makes that genuinely unsettling. This isn't a glitch. This isn't a failure. This is the system working exactly as designed. And if you stay until the end of this video, you'll understand exactly why that should concern every single one of us. Because the next one could be bigger, and we still won't see it coming. Subscribe and follow along, because this story does not end when the last meteorite is pulled out of a Medina County field. Space has been throwing objects at Earth. The rocks will keep coming. And when the next one announces itself by shaking your windows at 9 in the morning, this channel is where you'll get to know what actually happened and what the science actually says, including the parts that won't have clean answers yet. You are going to want to be here for that. Now let's get into it. On the morning of March 17th, 2026, at 8:57 a.m. Eastern Time, something extraordinary happened over northern Ohio, and almost nobody knew what it was. A streak of light tore across the sky above Lake Erie, moving faster than your brain could fully register it. Within seconds, it was gone, not because it passed, but because it exploded. And if you were standing anywhere near the Valley City or Medina area of Ohio that morning, you felt it before you understood it. The windows rattled, the floors shook, and your first thought was probably not Asteroid. Your first thought was probably, what just happened? Here is what happened. A 7-ton object from space entered Earth's atmosphere and detonated over the United States with the energy equivalent of roughly 250 tons of TNT. No warning, no countdown, no alert on your phone. Just a silent approach and then a shockwave that scared the living daylights out of an entire region. The part that should stop you cold is this. Humanity currently tracks thousands of near-Earth objects. We have telescopes, databases, international monitoring networks, and government programs specifically dedicated to finding things that might hit us. And yet, the one that actually did hit us, the one that actually exploded over a major American metropolitan area, was invisible to every single one of those systems until it was already detonating overhead. Not almost missed, not barely caught, completely, totally, 100% unseen, until it was already exploding. NASA and US government sensor data confirmed the event almost immediately after it happened. The military's classified satellite network registered it. The GOES-19 weather satellite's lightning mapper caught a massive brightness spike. Seismic instruments picked up the shockwave. People across 10 states plus Ontario, Canada, looked up and saw a fireball crossing the sky. 911 lines across northeastern Ohio were flooded, callers reporting what they thought was a bomb, an earthquake, a gas explosion, a plane crash. The explanations people reached for tell you everything. When something that large and that loud comes out of nowhere, the human mind scrambles for a framework that makes sense. A rock from space? That doesn't feel real. That feels like a movie. And that framing, that feels like a movie instinct, is exactly the problem. Because this has happened before. And when it happened before, it didn't end quietly. But we'll get there. For now, sit with this question, because it's the one that should genuinely unsettle you. If our detection systems couldn't see this one, a 7-ton object that exploded over American soil on a Tuesday morning, what else is out there right now that we aren't seeing? The system didn't malfunction. No alarms went off because no alarm was triggered. It worked exactly as designed. That's not reassuring. That is the problem. To understand why this event is as significant as it is, you need to understand what actually crossed the sky that morning, because the numbers involved are genuinely difficult to hold in your head. The object was approximately 6 feet across, about 1.8 meters. You could, theoretically, fit it in the back of a pickup truck. Its mass was around 7 tons. Think of a fully loaded military vehicle. By asteroid standards, this is not a giant. It is not even close to a giant. It is, by the definitions planetary defense scientists use, a small object. And that word small is going to mean something very different to you by the time this is over. It entered Earth's atmosphere at approximately 45,000 miles per hour. That's around 20 kilometers per second, or roughly Mach 58. Fighter jets top out around Mach 3. This thing was traveling nearly 20 times faster than that. At that speed, the atmosphere is not air. It is a wall. The object began compressing the air in front of it so violently that the air itself superheated to temperatures hotter than the surface of the sun. The object first became visible at around 50 miles altitude. It traveled approximately 34 miles through the atmosphere before it stopped being a rock and became an explosion. The breakup happened at an altitude of roughly 45 kilometers above the surface, and the energy released in that moment was estimated by NASA at between 0.25 and 0.37 kilotons, approximately 250 tons of TNT equivalent. To put that in terms you might actually feel, the largest conventional bomb in the United States military arsenal, the MOAB, the Massive Ordnance Air Blast Bomb, releases energy equivalent to roughly 11 tons of TNT. This asteroid released energy approximately 23 times stronger than that, and it was 6 feet wide. The reason there's no crater in Ohio is because the explosion happened in the air. This is what's called an airburst. The object doesn't need to reach the ground to cause damage. As it plows through increasingly thick atmosphere, the pressure builds faster than the rock can structurally handle, and it shatters, releasing all of that kinetic energy at once in a mid-air detonation. The energy goes outward and downward as a shockwave. The ground shakes. Windows rattle. People reach for their phones. Here's where it gets uncomfortable. Energy scales with size, but not linearly. It scales exponentially. Make this object twice as large, and you don't get twice the explosion. You get something far, far worse. A small asteroid can behave like a weapon of extraordinary scale because the kinetic energy baked into its speed is released all at once. And this 6-foot truck-sized rock is the smallest category we consistently, routinely, systematically fail to detect, which raises an obvious question about what happens when the next one is a little bigger. Let's slow this down and talk about what it actually felt like to be in northeastern Ohio that morning, because the human experience of this event is important, and it reveals something that the sensor data alone doesn't tell you. First, there was the light. For anyone who happened to be looking in the right direction, the sky produced a fireball, described by witnesses as a brilliant streak with a visible tail, like something falling out of the sky at speed, which is of course exactly what it was. Some described it as a flash, others caught it on dash cams, home security cameras, and weather monitoring equipment. The visual was striking and was over in seconds. Then, there was silence. Not because nothing was happening, but because sound travels much slower than light. Depending on how far you were from the airburst point, you waited. Seconds passed. In some cases, minutes. You might have seen the flash and thought it was lightning, or a reflection, or your imagination, and then the sound arrived. And what a sound it was. Witnesses described it as a deep, rolling rumble that built into something sharper, a crack, a boom, a percussion that hit the chest as much as the ears. Houses shook. Windows rattled hard enough to concern people. In some accounts, it felt like the ground moved, which is why earthquake was among the first guesses. The Medina County area, the Valley City region, and surrounding communities all felt the shockwave in varying degrees depending on proximity. Reports came in from across Ohio, into Pennsylvania, New York, Maryland, and beyond. The 911 calls are worth thinking about for a moment. When a sudden, unexplained physical event occurs, shaking, loud noise, a flash in the sky, the human stress response fires immediately. People called reporting explosions, gas leaks, aircraft incidents, tremors. Emergency services across multiple counties were fielding calls simultaneously. The infrastructure of local emergency response, designed for very human-scale crises, was briefly strained by an event that came from 200 miles up. Here is something worth noting. Most people experienced this event through sound, not sight. The fireball was visible, yes, but only if you happened to be looking at the right part of the sky at the exact right second. The shockwave, on the other hand, arrived in your walls, your floors, your chest cavity. For most people in that region, the asteroid made itself known not as a streak of light, but as an inexplicable, frightening physical sensation. Reality hit, literally, before understanding did. The human experience of this event lagged behind the event itself by minutes. And here's what makes that even more unsettling. The technology that recorded it, the dash cams, the weather satellites, the seismic instruments, all of it was reactive too. But even more unsettling than that is what the detection timeline actually looked like. Because the first data didn't arrive before the explosion. It arrived because of it. Every system that detected this event detected it after it was already over. Let that land for a moment. The United States military operates a network of classified infrared satellites designed, among other things, to detect missile launches and large energy releases. Those systems registered the March 17th airburst, but not until the detonation had already occurred. The GOES-19 weather satellite, operated by NOAA, carries an instrument called the Geostationary Lightning Mapper, or GLM. The GLM is designed to detect lightning. What it actually detected that morning was something far brighter, a massive optical spike over northern Ohio that no lightning bolt could explain. Again, this was registered after the airburst, not before. Ground-based seismic instruments across the region picked up the atmospheric shockwave as it propagated downward and outward from the explosion point. Seismic detection. Post-event. NASA's Center for Near-Earth Object Studies, CNEOS, maintains a database called the Fireball and Bolide Reports Table. It catalogs impact events from around the world, drawing on infrasound arrays, satellite data, and seismic networks. The March 17th Ohio event will appear in that database. And if you scroll through those records, you'll notice something consistent. Every entry is a historical record. Every single one is a thing that already happened. CNEOS is not a warning system. It is an archive. This is the distinction that matters more than almost anything else in this story. We are extraordinarily good at measuring impacts. Our sensor networks are sensitive, global, and sophisticated. They can tell you exactly how much energy was released, at what altitude, at what location, within hours of an event. What they cannot do is tell you 30 minutes beforehand that something is coming. For objects in the size range that hit Ohio on March 17th, we have, effectively, no predictive capability. We have a perfect rearview mirror. We have no windshield. Think about what that actually means in practical terms. An object entered the atmosphere and exploded over a populated area of the United States. And the only difference between scary news story and mass casualty event was the altitude at which it chose to detonate, a variable that no human decision influenced in any way. The system that's supposed to protect us from this kind of thing recorded it beautifully after the fact. The system worked exactly as designed, and that, more than anything else in Act 1, is why this matters. Because this isn't a rare failure mode. It is routine, And to understand why, you need to understand the gap that everyone in planetary defense already knows about, but cannot yet close. When people find out that a 7-ton space rock exploded over the United States without any warning, the natural assumption is that something went wrong. A sensor failed, a telescope was pointed the wrong way, someone missed a report. But that's not what happened. What happened is that the system performed exactly as it was built to perform, and the system was never built to catch something like this. NASA's Planetary Defense Program has a mandate, and it's a serious one. The agency has successfully cataloged more than 95% of all near-Earth objects larger than 1 kilometer. These are the objects capable of ending civilization as we know it, the extinction-level impactors. We know where the vast majority of them are. We can track them across centuries of orbital time, and none of the ones we've found are heading for Earth in any foreseeable future. That is a genuine, hard-won scientific achievement. Then there's the next tier down, objects in the range of 140 meters and above. These are sometimes called city killers, large enough to level an urban area or trigger regional catastrophe. There's ongoing work to find and catalog these, driven by congressional mandate and dedicated telescope programs. Funding decisions, mission priorities, international agreements. They all reflect the logic that the larger the object, the more catastrophic the consequence, and therefore the more urgently it deserves attention. That logic is not wrong, but it creates a gap, a real, measurable, documented gap that planetary defense scientists are not shy about acknowledging. Objects in the range of 1 to 20 meters, the range that includes the Ohio asteroid, fall below the effective detection threshold of the current global monitoring network. They are too small to reflect enough light to trigger alerts. They are too numerous to individually catalog. There are millions of them in Earth-crossing orbits, and we have no practical way to track them one by one. The Ohio asteroid, at approximately 1.8 meters, sits comfortably inside this blind zone, not at its edge, squarely inside it. This is not a bug in the system. It is a feature, a deliberately accepted limitation, based on a rational allocation of resources and risk. The problem is that rational and safe are not always the same thing. And there's one more factor that makes this blind zone even larger than it already sounds. Because there's a direction from which objects can approach that makes them essentially invisible. Not because our telescopes aren't good enough, but because of where the sun is. Ground-based telescopes, almost without exception, must look into dark sky to function. That's not a technology failure, it's physics. You cannot point an optical telescope toward the sun, or anywhere near it, and expect to detect a faint, fast-moving object in that glare. It would be like trying to spot a moth flying toward a searchlight by staring directly into the beam. The moth is real. You simply cannot see it from that direction. This creates what planetary defense researchers call the sunward blind spot. Objects approaching Earth from the direction of the sun, from what's called the interior of Earth's orbit, or from angles that place them close to the solar disk in the sky, are functionally invisible to ground-based survey telescopes during their final approach. And here's the cruel geometry of it. The most dangerous approach vector is often the sunward one, because objects coming from that direction tend to arrive quickly, with little or no observational window, even in principle. When a fireball occurs during daylight hours, that is one of the strongest indicators that the object came from the sunward direction. The Ohio airburst happened at 8:57 in the morning. Daylight. The approach geometry fits exactly. This is not a new problem. The Chelyabinsk meteor, the last major event before Ohio, and the one that injured 1,500 people in Russia in February 2013, approached from within approximately 15 degrees of the sun. No telescope on Earth tracked it beforehand, for exactly this reason. 13 years later, the same blind spot claimed another object. same failure mode. Different country. We're going to talk about Chelyabinsk in detail in a moment, because the comparison to Ohio tells you something important about scale that the raw numbers alone don't fully communicate. Solutions have been proposed. The most serious is a space-based telescope called NEO Surveyor, a NASA mission specifically designed to survey the sky from a position that eliminates the sunward blind spot problem by operating from the vicinity of the L1 Lagrange point between Earth and the Sun. It's a genuinely good idea. Progress has been made, but it is not yet operational. And even with it, the coverage limitations for very small objects remain significant. Because even if you could see them in time, even if you spotted the rock at distance and had warning, there's a second problem that doesn't get talked about enough. One that has nothing to do with telescopes. It has to do with speed. 20 kilometers per second. That is how fast the Ohio asteroid was traveling when it hit the atmosphere. Let's make that concrete. At that speed, the object traversed the entire visible thickness of Earth's atmosphere, from first contact to detonation, in a matter of seconds. Not minutes, seconds. Now imagine you have a telescope, and that telescope detects this object when it's, let's say, 10 minutes out. That is a genuinely optimistic scenario for an object of this size, but let's grant it. What happens in those 10 minutes? Automated alerts fire. Computer systems flag the detection. Notifications begin routing through planetary defense communication chains, national emergency management agencies, civil defense systems. By the time a human decision maker receives an actionable alert, by the time the word incoming reaches anyone with the authority to do something about it, the object is already exploding. 10 minutes is not enough time to evacuate a city. It is barely enough time to send a text message through bureaucratic channels. For objects in the size range of what hit Ohio, the realistic detection to impact window, even under best-case conditions, is measured in minutes, possibly seconds. That's not a detection problem. That is a physics problem. The object is simply moving too fast for any human response system to act meaningfully between we see it and it's here. Compare that to the missile warning systems that Cold War planners built their strategy around. Those gave you roughly 20 to 30 minutes. Enough time, in theory, for decisions to be made. An asteroid of this size gives you no such luxury. And unlike a ballistic missile, an asteroid does not broadcast a launch. It does not emit a radar signature that triggers detection the moment it leaves the ground. It is a dark rock in dark space, silent and uncommunicating, until it is suddenly very, very loud. Detection is not prevention. This is the uncomfortable truth at the center of planetary defense for small objects. Even a perfect detection network, one that caught every rock in this size range, would, for objects moving at these speeds, provide little more than a few minutes of warning. Enough to be terrified. Not enough to do much about it. And you might be tempted to think, fine, but how often does this actually happen? Surely this kind of event is rare. The answer to that question is probably not what you're expecting. Every single day, Earth is struck by approximately 80 tons of extraterrestrial material. Let that sit there for a second. 80 tons. Per day. The vast majority of it burns up invisibly in the upper atmosphere. Dust, sand grain-sized particles, tiny fragments that never make it close to the ground. But the picture changes as you scale up. Objects roughly the size of a car, similar in mass class to the Ohio rock, are estimated to enter the atmosphere roughly once a month somewhere on Earth. Monthly. Objects large enough to produce visible, notable fireballs, detectable by sensor networks, happen multiple times per year. Actual airbursts of meaningful energy, events in the range of what happened over Ohio, or larger, occur on a timescale of years, not decades. Most of these events happen over oceans, which cover about 70% of Earth's surface. Others happen over remote land areas with no witnesses and no cameras. Many go completely unrecorded in any public database because there's simply no one there to see them, and the sensors, while good, are not omnipresent. The global population is not evenly distributed, which means the probability of one of these events occurring over a major urban center on any given day is low, but it is not zero. It has never been zero. And as camera coverage of the planet's surface increases, dash cams, security systems, satellite imaging, weather monitoring, our awareness of these events is growing faster than the events themselves are. This can create the impression that something is accelerating, that things are getting worse. The reality is more complicated. We are getting better at noticing what was always happening. But here's the risk framing that planetary scientists use, and it's worth understanding. Low probability plus high consequence is not the same as low risk. A 1% chance of something that injures thousands of people is a risk that rational societies spend serious money to reduce. The Ohio event fell on the low consequence end of the spectrum because of its size, its altitude of detonation, and the fact that it exploded over a relatively rural stretch of northeastern Ohio rather than downtown Cleveland. Change any one of those variables, and the conversation changes completely. We've seen what happens when the object is bigger. We have the data. The name of that data is Chelyabinsk. On February 15, 2013, the residents of Chelyabinsk, Russia, a city of over 1 million people, woke up to an ordinary winter morning. It was just after 9 a.m. local time when the sky above them turned brighter than the sun. The object that caused it was approximately 20 meters across. That's roughly 65 feet, big enough to fill a modest house. It entered the atmosphere at around 19 kilometers per second, moving in a shallow trajectory that allowed it to travel deep into the lower atmosphere before it broke apart. The energy released in that breakup was staggering, estimated at between 400 and 500 kilotons, not tons of TNT kilotons. For reference, the atomic bomb dropped on Hiroshima released approximately 15 kilotons. The Chelyabinsk airburst released somewhere between 25 and 30 times that energy, and it exploded in the sky, miles above the city. The flash was so intense that people who looked at it received UV burns, essentially sunburn, on exposed skin in the middle of a Russian winter. The shockwave arrived minutes later and shattered windows across an area of thousands of square kilometers. Approximately 1,500 people were injured, the vast majority from glass lacerations. People who had walked to their windows to watch the light in the sky were still standing there when the blast wave arrived. Factory walls collapsed. Building facades cracked. The damage bill ran into hundreds of millions of dollars. All of this from an object that exploded in the air without touching the ground. And here's the thing you probably already guessed. No telescope saw it coming. Chelyabinsk approached from the sunward direction. The approach angle placed it within the sun's glare throughout its final approach, invisible to every ground-based survey telescope on Earth. The same blind spot, the same failure mode, the same fundamental problem, on a day when the answer wasn't shockwave felt across 3 counties. The answer was 1,500 injuries and an entire Russian city picking glass out of its walls. 13 years before Ohio. Same mechanism. And yet the gap remains. You now have 2 data points. The Ohio asteroid, roughly 1.8 meters across, releasing energy equivalent to about 250 tons of TNT, and Chelyabinsk, approximately 20 meters across, releasing energy equivalent to 400 to 500 kilotons. The size difference between those 2 objects is roughly a factor of 10. The energy difference is a factor of roughly 2,000. Read that again. 10 times larger, 2,000 times more energetic. This is because energy scales not with size, but with volume, and volume increases as the cube of diameter. Make an object twice as wide, and it is 8 times the volume, and therefore roughly 8 times the mass. But kinetic energy also scales with mass, so the relationship between size and destructive potential is not linear. It is explosive. It accelerates. A golf ball versus a car versus a building, the visual difference seems incremental. The physical consequence is not. Think about that scaling law when you consider the Ohio object. At 6 feet across and 250 tons of TNT equivalent, it shook buildings and rattled windows over a wide area. Now imagine that object was not 6 feet across, but 12 feet, 20 feet, 40 feet. Each step up the size ladder doesn't add damage in a proportional way. It multiplies it. The jump from Ohio scale to Chelyabinsk scale is not a jump from scary to scarier. It is a jump from regional news story to mass casualty event. And there's an obvious, uncomfortable question that this scaling law forces you to ask. What if the March 17th object had been just slightly bigger? Not Chelyabinsk sized, just bigger. What if it had been 12 feet instead of 6? What if it had detonated, not over rural Medina County, but over a city? Cleveland, Ohio sits roughly 30 miles west of where the March 17th airburst occurred. Its metropolitan population is approximately 2 million people. Downtown Cleveland contains some of the most densely packed urban infrastructure in the Midwest: office towers, hospitals, schools, sports arenas, highway interchanges. It is, by any measure, a major American city. If the Ohio object had been Chelyabinsk-sized, 20 meters instead of 1.8, and had detonated at a similar altitude over the Cleveland metropolitan area, the primary mechanism of injury would have been the same as in Russia: glass. Thousands of windows in high-rise buildings, residential structures, and commercial properties shattering simultaneously and projecting glass shards inward at speed. The shockwave from a 500 kiloton airburst does not knock buildings down in most scenarios, but it absolutely shatters glass across an enormous area. In a city the size of Cleveland, on a weekday morning with buildings full of workers, the number of people standing near windows at the moment of impact would be difficult to calculate, and the injury toll could easily reach into the thousands. Emergency services would be overwhelmed. Hospitals, many of which would themselves have sustained window damage, would be managing mass casualty intake. Transportation networks would seize up. The economic disruption would be measured in billions of dollars and would persist for months. None of that happened. The object was 6 feet wide, not 60, and it detonated over farmland and suburban stretches of Medina County rather than over a downtown core. Geography saved us. Not preparation, not detection, not planetary defense. Geography and object size. The variables that determined the outcome of the March 17th event were entirely outside human control. And if you find that unsettling, you should, because we have known about this specific combination of blind spot and scaling risk since at least 2013. And yet, here we are. After Chelyabinsk, the world's space agencies and governments paid attention, at least briefly. Congressional hearings were held. Funding was increased. NASA stood up its Planetary Defense Coordination Office. The DART mission, the Double Asteroid Redirection Test, was funded, launched, and successfully demonstrated in 2022 that a spacecraft could alter the orbit of an asteroid through kinetic impact. That is a genuine achievement, and it matters enormously for objects that are large enough to detect far in advance. New survey telescopes were funded and planned, but the focus remained where it had always been, on the large end of the size spectrum, on the objects that, if they hit us, would end things in an extinction-level way. The rationale is defensible. These are the worst-case scenarios, and if you can only protect against one threat at a time, you start with the existential one. The problem is that the lesson Chelyabinsk actually demonstrated was not about extinction-level objects. It was about medium-small objects in the 20 to 100 meter range. objects too small to easily track, too large to be harmless, and approaching from a direction we systematically cannot observe. That lesson was acknowledged. It was studied. Papers were written. And then the detection gap for objects in that size range remained essentially unchanged for 13 years. The same gap swallowed the March 17th object as cleanly as it swallowed Chelyabinsk. The same event could happen again tomorrow. Not eventually. Tomorrow. And there is nothing currently operational that would change the detection outcome. No warning, no tracking, no alert, until it's already over your head. But there is something interesting about the March 17th event specifically. Something physical, something you can hold in your hand that makes this particular impact different from most. Because this one left something behind. When a large enough meteoroid survives its passage through the atmosphere and produces an airburst, fragments of the original object sometimes make it to the ground. These are called meteorites, the technical term for what survives. Not all airbursts produce them. The breakup dynamics have to be right. The object has to be structurally heterogeneous enough that some pieces don't fully combust, even as the rest of the mass explodes. The survival rate is estimated at somewhere between 5 and 10% of total events. In the case of the March 17th Ohio airburst, NASA confirmed that meteorites did reach the ground. The strewn field, the elongated ellipse of territory across which fragments land, shaped by the object's trajectory and wind conditions, covers parts of Medina County, Ohio. The physics of how a strewn field forms is worth understanding. As the object breaks apart at altitude, individual fragments of different masses separate. Heavier pieces travel farther along the original trajectory. Lighter, smaller pieces are more quickly slowed by atmospheric drag and fall more steeply. The result is a distribution pattern that, when mapped, allows scientists to reconstruct the breakup event in significant detail. Direction of travel, angle of entry, approximate mass distribution of the original object. Meteorite hunters with GPS-equipped equipment can use the modeled strewn field to search systematically. In famous falls, recovered meteorites have sold for thousands of dollars per gram. More importantly for science, each recovered fragment is a sample of the original impactor, a piece of the actual object that crossed our sky without warning. There are physical remnants of an invisible threat sitting in the fields and roadsides of Medina County right now. Some have probably already been found. Others are waiting. And what those pieces are made of tells us something important, not just about this particular rock, but about why the outcome was what it was. The composition of an asteroid or meteoroid is one of the most consequential factors in determining what happens when it enters the atmosphere. Not all rocks are created equal, and in the world of hypervelocity, atmospheric entry, structural strength can mean the difference between an airburst at 45 kilometers altitude and an object that drives itself much deeper into the atmosphere before releasing its energy. Based on the altitude of the Ohio airburst and the dynamics of the event, the object was most likely a stony meteorite, either an ordinary chondrite or a similar silicate-rich composition. These are the most common type of near-Earth objects. They tend to be relatively fragile at the scale of atmospheric entry physics, meaning they break apart at higher altitudes where the atmosphere is still thin. This is actually, counterintuitively, sometimes protective. A high-altitude airburst distributes energy over a wider area at lower intensity, rather than focusing it closer to the ground. The Chelyabinsk object was also a stony meteorite, and its fragility contributed to a high-altitude breakup that, while still producing enormous damage through the shockwave, did not result in large fragments striking the ground at terminal velocity. Contrast that with iron or stony iron meteorites, objects with significantly higher structural strength. These can penetrate much deeper into the atmosphere before they break apart or reach the surface. An iron impactor of similar mass to the Ohio object might have behaved very differently, potentially reaching lower altitudes, or even the ground itself before releasing its energy. The composition, in other words, is not just a scientific curiosity. It is a damage-determining variable. And we don't know the composition of an object until we can study it, which, for undetected impactors, means we don't know until after the fact. But the composition question leads to a deeper one. Where did this thing come from? Because the answer to that question reveals something about just how typical this event actually was. The solar system is not a clean, orderly place. The asteroid belt between Mars and Jupiter contains hundreds of millions of objects ranging from grains of dust to bodies hundreds of kilometers across, and it is not stable. Gravitational interactions, primarily with Jupiter, which is massive enough to significantly perturb orbits across the inner solar system, cause collisions, fragmentations, and orbital drift over geological timescales. Pieces break off larger bodies. Fragments drift into resonance zones, where the math of orbital mechanics gradually shifts their paths. Over millions of years, some of those fragments migrate into Earth-crossing orbits. They become near-Earth objects, and some of them eventually find Earth. The Ohio object was almost certainly a fragment of this kind, a piece of the inner solar system's background debris population, displaced from a stable orbit in the asteroid belt at some point in the ancient past, slowly drifting into its March 17, 2026 appointment with Earth's atmosphere. Its trajectory through space before that moment may have been tens of millions of years in the making. And here's the thing about that. This object was not special. It was not unusual. It was not a 1 in a billion event. Near-Earth space is full of objects like it, in the same size range, the same composition class, the same orbital population. The count of near-Earth objects in the 1 to 20 meter range is estimated in the millions. Most of them will never come close to Earth. Some of them will. We cannot track them individually. We never will be able to, with current technology. The Ohio asteroid was not a rare visitor from a distant corner of the solar system. It was one of our neighbors. One of millions. And most of the time, when one of those neighbors makes contact with Earth, we never hear about it at all. Consider the geometry of this planet. Approximately 70% of Earth's surface is covered by ocean. Of the remaining 30%, significant portions are remote. The Amazon basin, the Sahara, Siberia, Central Australia, the Tibetan Plateau, Antarctica. The vast majority of Earth's land area, by surface coverage, is either uninhabited or very sparsely populated, which means the vast majority of impacts like the Ohio event go completely unwitnessed by human beings. No dashcam footage, no 911 calls, no seismic readings close enough to the source to pinpoint it. An airburst over the South Pacific at 2 in the morning produces a flash that no one sees, and a shockwave that no one feels, and a strewn field that sinks into 4,000 meters of water. It happened. It will not appear in your newsfeed. The CNEOS database contains records of hundreds of bolide events detected by government sensors since the 1990s, the vast majority of them over oceans or remote regions. These are just the ones the sensor network caught. The actual rate of such events is higher than the detected rate by an unknown margin. This detection bias, the fact that we're far more likely to notice events near populated areas with good sensor coverage, shapes public perception of how often this happens. People assume it's rare because they rarely hear about it. It is less rare than that assumption implies. Think about a version of Earth with 10 billion people, spread uniformly across every habitable surface, each with a smartphone and a dash cam. How many events per year would trend globally? How different would our sense of this threat be if every impact over every ocean was recorded? We don't know. We genuinely don't know. The data we have is shaped by where we're paying attention. But something is happening right now in 2026 that's making planetary defense researchers pay attention a little more carefully than usual, because the Ohio event was not the only thing that hit the news in March of 2026. In the weeks surrounding the March 17th Ohio airburst, other notable fireball and meteorite events were reported across different parts of the world. A European meteorite strike attracted attention. Fireball sightings were logged across multiple regions of the United States. Planetary science social media accounts, which have, in the past decade, become a genuinely useful informal monitoring system, lit up with reports, videos, and discussion. And the question that started circulating, quietly at first and then more loudly, was whether this represented a genuine clustering of events or whether it was something more mundane. Better cameras, more people looking up, and social media creating the impression of a pattern in what was actually random noise. This is a legitimate and important distinction. We live in an era of exponentially increasing camera coverage of the planet's surface. Dashcams alone have transformed fireball documentation in the past 15 years. Events that would once have been reported only as vague eyewitness accounts are now captured in high-definition video from multiple angles simultaneously. Security cameras, doorbell cameras, all-sky meteor monitoring networks, smartphone video, the infrastructure for recording unusual sky events is orders of magnitude better than it was even a decade ago. More events being recorded does not mean more events are occurring. It may simply mean we are recording a larger percentage of what was always happening. The honest answer, as of March 2026, is that separating genuine statistical clustering from reporting bias requires more data and more time than is currently available. Scientists are cautious about this, as they should be. Pattern recognition is something human brains do instinctively and often incorrectly, especially when the pattern is emotionally compelling. But the caution cuts both ways. Some of the details emerging from the broader March 2026 context are harder to explain away as pure coincidence. And there is one specific hypothesis that has started circulating, not in fringe corners of the internet, but in actual scientific discussion, that deserves to be laid out clearly, with all of its caveats attached. Random events cluster. This is not intuitive, but it is mathematically true. If you flip a coin 1,000 times, you will see runs of 6 or 7 heads in a row. Not because the coin is biased, because randomness is not uniformly distributed. Clustering is what random looks like when you're watching it happen. Planetary scientists who work with impact frequency data are very familiar with this principle. They will tell you, correctly, that a week or two of elevated fireball reports does not constitute statistical evidence of a genuine spike in Earth's bombardment rate. The sample size is too small. The detection coverage is too uneven. The reporting infrastructure is too dependent on geography and media cycles to provide reliable global numbers over short timescales. At the same time, multiple confirmed impacts in a short window are notable enough to warrant serious analysis, even if that analysis ultimately concludes that the clustering was random. The scientific process here is not to dismiss the question, but to ask it rigorously. Are the events correlated in direction? Are they coming from similar orbital geometries? Do the chemical compositions of recovered meteorites suggest a common parent body? These are the questions that real researchers are working on with the actual data, and as of now, definitive answers are not available. What is available is one particular hypothesis, speculative, not confirmed, but not scientifically absurd, that might explain an elevated rate of encounters if it turned out to be true. In the summer of 2025, astronomers detected what appeared to be a third known interstellar object passing through the solar system. Designated 3I Atlas, it attracted significant scientific attention. Unlike the solar system's native population of asteroids and comets, interstellar objects originate outside our solar system entirely, approaching from the broader galaxy and making a single hyperbolic pass through our neighborhood before continuing outward forever. The first confirmed interstellar visitor, Oumuamua, was detected in 2017. The second, Borisov, in 2019. 3I Atlas was, if confirmed, the third. Here is where the hypothesis enters. Some researchers have raised the question, tentatively, with significant caveats, of whether an interstellar object on a close pass through the inner solar system might shed debris, whether its passage might disturb small populations of material, or whether the object itself might have a loose coma of small particles that could intersect Earth's orbit as the object's trajectory crosses through the inner solar system. This is speculative. It is not confirmed by NASA. There is currently no established scientific evidence directly linking 3I Atlas to the March 2026 fireball events. The orbital mechanics would need to be worked out in detail for any specific hypothesis to be testable, and that work is ongoing. But here's why it's worth mentioning. Not because it's proven, but because it represents the kind of question that a genuinely uncertain situation generates. If an interstellar object's debris trail were intersecting Earth's orbital path at this moment, the risk profile would be meaningfully different from background bombardment, and it would be temporary. We might be in an elevated risk window that will pass, or we might simply be experiencing ordinary random clustering and looking for patterns where none exist. The point is, we are currently mid-analysis, not post-conclusion. The situation is unresolved. And unresolved is an uncomfortable place to be when the subject is rocks falling from space. If it turned out, through rigorous analysis, not speculation, that the March 2026 fireball cluster reflected a genuine temporary elevation in Earth encounter rates, the implications would be significant and immediately practical. Planetary defense agencies would face an uncomfortable problem. An elevated bombardment rate from small objects provides essentially no additional warning time compared to the baseline. The objects are still too small to detect in advance. The approach vectors are still subject to the sunward blind spot. The response infrastructure is still calibrated for large object threats. Being in an elevated risk window would mean heightened probability of an event, with no corresponding increase in our ability to detect, warn, or respond. The monitoring priority would intensify. Fireball network operators, seismic array managers, and satellite data analysts would be watching more carefully. Research into the 3I Atlas orbital mechanics and any potential debris association would be accelerated. Public communication protocols would be internally reviewed. And at the same time, publicly, most people would have no idea that any of this was being discussed, because the science is too uncertain to communicate without causing disproportionate concern. This is the reality of planetary defense in the small object regime. The threat is real. The detection is reactive. The communication infrastructure is designed for large objects with long lead times, not for events that can occur with no warning at all. We may be mid-event, not post-event. The March 17th Ohio airburst may be a standalone data point in an otherwise ordinary distribution, or it may be one entry in a short but elevated series. We genuinely do not know yet. And the honest acknowledgement of that uncertainty leads directly to the largest question this entire story has been building toward. Not about this particular rock, or this particular month, but about the broader reality of where we stand. Here is the most important thing to understand about planetary defense as it currently exists. It is incomplete by design, not by accident, not because of negligence, by deliberate, documented, rational choice, and that rationality has a cost that the March 17th event just put on display. The logic runs as follows. Resources are finite. The most catastrophic possible outcome is an extinction-level impact, a kilometer-scale object that ends civilization. Preventing that outcome is worth an enormous investment. Below that, the calculus of consequence guides investment downward. City-killer objects in the 140-meter range, worth significant investment, currently the subject of active survey programs. Objects in the 50 to 100-meter range, acknowledged risk, limited dedicated resources. Objects in the 1 to 20-meter range, formally acknowledged as below the practical detection threshold, largely unaddressed, treated as background noise. This is not a secret. The planetary defense community has published this prioritization openly. The Torino scale, the Palermo scale, the congressional mandate for the Space Guard survey, they all reflect the same fundamental logic. Prioritize by worst-case consequence. The problem is that this approach optimizes for preventing extinction while leaving a persistent, unaddressed gap for events that can injure thousands of people, destroy infrastructure, and cause mass panic. Disruption is not extinction. But disruption is not nothing. We built a system that protects us from the end of the world, and in doing so, accepted that we would be largely helpless against events like Chelyabinsk and Ohio. That is not a criticism of the people who made those choices. They were reasonable choices under real resource constraints. It is an observation about what those choices mean in practice, and what the March 17th event demonstrates about the gap between reasonable and sufficient. There is one more element to the broader context of mid-March 2026 that deserves mention, not because it's directly related to the asteroid, but because it layers onto the overall picture in a way that is genuinely worth understanding. In the days surrounding the Ohio airburst, solar activity was elevated. Coronal mass ejections, massive eruptions of magnetized plasma from the sun's corona, had been tracked heading toward Earth, with arrivals anticipated around March 19th, coinciding with the spring equinox. Equinox periods are associated with enhanced geomagnetic activity because the geometry of Earth's magnetosphere relative to the solar wind becomes more favorable for energy transfer during these alignments. To be completely clear, a coronal mass ejection has no physical relationship to an asteroid impact. The sun's plasma output and a space rock's trajectory are governed by entirely different physics and are causally unconnected. The CME timing was a coincidence, not a correlation. But human psychology does not always process coincidences as coincidences when they arrive in clusters. A major asteroid impact on March 17th. Enhanced solar activity and potential geomagnetic storm conditions arriving 2 days later. Multiple fireball events across the same general period. Each of these, individually, is explicable and within the range of known natural variability. Together, in the span of a week, they create a psychological stacking effect that amplifies the sense of threat beyond what any single event would generate alone. This matters for how the public and media respond to these events, and how science communicators need to navigate the difference between several unusual things happened in the same week, and these unusual things are connected. They are not connected, but the feeling that they might be is worth acknowledging, because that feeling shapes public attention and political will in ways that can actually affect what resources get allocated to planetary defense. Attention, even misattributed attention, is not always useless. The real limitation, though, the one that no amount of media attention fully resolves, is not funding. It's physics. The Ohio asteroid was 6 feet across. It released energy equivalent to 250 tons of TNT and shook buildings across a region of northeastern Ohio that includes hundreds of thousands of people. No one was killed. No one was seriously injured. The story ended, for most people, as a remarkable piece of news about a fireball, a few days of discussion, and then the next news cycle. Now, scale up. 60 feet across, the lower end of what Chelyabinsk was. You are no longer in alarming near-miss territory. You are in 1,500 injuries, hundreds of millions in damage, a major city in crisis territory. We know this because it happened. In 2013, with no warning, 200 feet across, the range where an airburst over a dense urban center produces casualties measured not in hundreds, but potentially in tens of thousands, depending on time of day and geography. 600 feet. Then, beyond that, into the range where the conversation changes from disaster to catastrophe. The scaling law does not care about our detection capabilities. It does not care about our funding levels, or our political will, or our scientific sophistication. The math is the math. Larger objects carry energy that increases as the cube of their diameter, and when that energy is released in seconds over a populated area, the physics of it does not negotiate. We did not get lucky on March 17th, 2026, because we were prepared. We were not prepared. We got lucky because the object was small, because it detonated at altitude, because it chose, if a rock can be said to choose anything, a patch of rural Ohio over a downtown core. Luck is not a planetary defense strategy. It is not a system. It is not a plan. It is what we are currently relying on for the entire lower end of the impactor size spectrum. The next object in this size range will not announce itself. It will not show up in a tracking database or trigger an alert on your phone. It will enter the atmosphere at Mach 50-something, compress the air below it into a wave of pressure, and then it will either explode harmlessly at altitude or it won't. And the variable that determines which of those outcomes occurs will be the same one that saved northeastern Ohio on a Tuesday morning: size, angle, and a quantity of luck that has no guaranteed supply. We are not watching the sky for this one. We were not watching for the last one. And somewhere out there, in the sunward blind spot where our telescopes cannot look, something we cannot see is moving. It is not asking for permission. It is not broadcasting a signal. It is just moving, the way rocks have moved through this solar system for 4 billion years, indifferent and silent, on trajectories that were set before the first human eye ever looked up and wondered what all those lights were. The difference between a story and a catastrophe is just size, and we won't know which one is coming until it's already here.